Okay. All right, let's start lecture. Okay. Okay, before we start the lecture, just want to mention of a few things. I don't think the Mac is working as good as previously, so okay, I'll just can people in the back hear me? Yeah, okay. Just a few feedbacks from the marking for first assignments from TA. Okay, yeah. One of the TA reported to me saying that she noticed that for some of the students, the writing, the solution, or basically assignments, are strikingly similar to the solution I gave you to the TA. Okay, I think I mentioned this in the first lecture. So it's impossible to come up with different questions for each year. So it's inevitable that the solutions is out there, right? And it's very natural that you probably have your buddies. You probably have got hold of this solution from previous year. But I said that's fine. However, what's not fine is you just simply jot it down, right, without your own due diligence type of work. Okay, so if you were caught, the TA has a suspicions that you are just simply copying the solution, or even just simply copying other people. Sometimes I probably have to call you to my office, okay, just to give you a warning. And most important part is this is exercise, right? If you don't do it, if you're just copying, guess what? During exam, that's where the consequence will come to you, right? Okay. So just want to bring it to your attention here. Okay. Let's tie up a couple loose ends on the parametric equation. Then we'll continue on the new topic, basically derivatives, integrals with respect to the vector functions. Okay. Oh, another thing I want to mention is next week we're going to have our first quiz. Okay. The first quiz will be held in the tutorial section. You should go to your tutorial section. If you can, for whatever reason, let me know. Maybe you can join another tutorial section just to finish the quiz, right? There will be 3 quizzes. This is going to be the first one. It's a question, just one question. It will be on planes and lines. Okay. The format of the quiz is actually open notes, so it's open. You can actually discuss with your classmates. Okay. The TA will just basically go over part of the tutorial, and then you have 25 minutes to finish those one question quiz. Okay. Yeah. So that just heads up for next week. Okay. So in the previous lecture, we talked about the parametric equation, and basically, if you have a curve C, okay, and we can represent the curve C, okay, using a position vector. So this position vector represents the movement of the position of a location, basically point P, which has a coordinates x of t, y of t, and z of t. So the parametric equation basically is to come up with 3 expressions describing the motion or describing the trajectory for this point P. The 3 equations representing it here is in terms of parameter t, so it could be different parameters. So that'll basically the idea of it is of getting a parametric equation for curve C. So in the previous lecture, what we reviewed here, we looked basically at parametric equation for some common curves. Okay, as I mentioned, there isn't a very systematic approach to derive this parametric equation, but often in time, for some of these very well-known curves, that's basically what you essentially wanted to remember, or just to know what the parametric equations are, right? So I just wanted to know what the expectations here is. Okay, number one, you need to basically know how to parameterize common curves. So common curves, for example, like a circle, okay, or typical function, let's say y equal to f of x. So the simplest way for this one, you can let the x equal to t, and then the y is just the rest of the expression is the parametric equation, right? So circle, y equal to x of t, or straight line. So this straight line basically means giving you, let's say, 2 points, right? Like the example that we did in the previous lecture. So asking you to go from here to here, and then go right here to here. So you have a C1, C2. So you have you have those given points. What could you do, right, to quickly derive a parametric equation for the straight line set here? So you don't actually need to go over those lengthy procedures deriving a line equation. So often in time, by just examining it, and you'll be able to derive this parametric equation at here, right? So this is basically the expectation for very common ones. This is essentially in the lecture, in the exams, for very common curves, and you need to know what are the parametric equation for that, because you probably need that for further steps of calculations, right? And the second one here, I also want you to understand is parametric equation. There are 2 aspects regarding this parametric equation, right? So basically, there are 2 faces or 2 sides of story, okay, on the parametric equation. One is, it's just simply a trajectory. Okay, it's simply just trajectory. So the parametric equation describes a certain trajectory, a circle, a straight line, right? But then another one is basically, it not only describes trajectory, you're using it to also describe certain type of motion, right? Okay, so there are two aspects of this parametric equation. So for example, I think I mentioned in the previous lecture for the last example right here, so that maybe just quickly go over it again. Suppose P1 is 1, 1, 0, and this is 1, 1, 1. Okay, so the way we draw it here is, okay, we draw it from, this is basically go from P1 to P2. Okay, this is a C2 at here, right? So this is the way we draw it here. So if you go from PC to P1 to P2, as we say, okay, so X, Y is not changing, it's still 1, 1. Only the Z is changing from 0 to 1. So one possible parametric equation is X of t equal to 1, Y of t equal to 1, and Z of t equal to t. Right? So then in this case here, if you let the Z of t equal to t, your range of the t is actually go from 0 to 1, right? Because that's exactly describing the motion from P1 to P2. Okay, yeah. Or you could just simply use a slightly different expression for the Z component. But then in this case, if you use 2t, so your range of the t will go from 0 to what now? 0.5, right? So that's something, see, this is a different, basically, type of motion. This definitely moving faster than this one at here, right? Yeah. And the other type, for example, let's say if a C2, instead of going from P1 to P2, let's say it goes from P2 to P1, right? So that's a completely different motion, but the same trajectory, isn't it, right? Same trajectory. So your parametric equation For y of txt, no change. But then your z of t, it would become 1 minus t now, right? So your t's range still, you see, okay, go from 0 to 1. So at the t equal to 0, it's at p2 location. At t equal to 1, it's at the p1 location. Okay, so that's the idea when it comes to the parametric equation. It's not just you come up with a solution. It's actually you come up with a solution that depicts the actual question there. Okay, yeah. So just make sure that you understand the two different sides on parametric equation, right? Yeah. Parametric equation is a very useful tool. Sometimes you can use it to actually describe fairly complicated curves, which you probably can't describe it in using a Cartesian equation. So I'll give you one more example here. So see that I have a parametric equation such like this. Okay, so we have a parametric equation giving it here. By looking at these two expressions, okay, this is in term parameter theta. Okay, we'll never be able to tell what exactly does it describe, right? This is such a weird functions with all the exponentials and the trigonometry functions involved in the two expressions that are here. Okay, so that's a parametric equation. Now, if I try to show you or draw it, okay, so. It's okay, I'll let you finish writing it here. So we're attempt to draw it, basically draw these coordinates x and y as the theta is changing. Computer is a bit slow. It's almost there. Yeah. Yeah, it keeps going. So if we don't stop, it'll just keeps going. So ultimately, it will generate a butterfly type of curves. Okay, so that such a sophisticated expression end up with a beautiful butterfly right here, right? This is basically often in time, the complication of the nature could be described by some crazy mathematical expressions. Okay, yeah. So just to give you an idea, right? And later, when we learn surface, I'll give you some more examples for using parametric representation. In a Cartesian, it's impossible. But if you use a parametric equation, then you have a chance to actually describe that. Okay. Yeah. Okay. So let's move on here. We basically looked at the parametric equation. So now let's formally introduce this parametric equation. Actually, basically, it's a so-called vector function. Okay, yeah. The definition at here is essentially given a vector, r of t, and t is a variable. So r of t is defined for each value of t. and let's say t has a range between a and b. So that's a vector. At the same time, the vector of r of t is a function of t, which is basically what we have seen, right? That's the parametric equation. Okay, yeah. So then we call this r of t basically is called vector function of t, okay, over this range AB. Okay. So that's the formal definition. I feel like we just need to write it down here, even though that sometimes we've been using it, we know what it is, right? It's just to have a formal definition for vector function at here. Okay. It's very much similar to the definition of a regular scalar function, right? So if you recall that for scalar function, so then you probably have f of x, okay? Or later we'll have a multivariable scalar function. Okay, so those are scalar function examples. Okay. Scalar function, I mean, in terms of function, the idea whenever you see the word function, basically the first thing coming to mind is function basically means you plug in three numbers, for example this one, three numbers here or two numbers here or one number here, it'll return one number back to you, right? Yeah, that's function. And you learn in 246, and then often in time you can think of the function as a certain system. So you plug in two inputs to the system, and then the system spits out one output, right? So that's a function, okay, representing a system. So then, what about the vector function? So if we have vector function, say that we have v of t at here. V of t basically has three components. Okay, so that's one example vector function. So basically, you plug in one parameter t, it'll return back, instead of just a scalar quantity, it'll return back what? A vector at here. Okay, so that's a vector function. You could also have written this scalar function as, for example, this one. So v is a vector function, but this is a function in terms of, instead of just a t, it's in terms of x, y, z. And of course, x, y, z could be just basically x of a t, y of a t, and z of a t. Right? Okay. So vector function, not much different from the concept of scalar function, except that the return for this vector function is not a scalar; it's a vector at here, right? So that's a vector function. Okay. So if you think about the room temperature at each location inside the room, so you can represent the room temperature maybe using a function of three variables. So temperature is a function of 1, 2, 3, the coordinates, right? Okay. But if you let's say wanted to describe the flow of the water, okay? So you pick a point inside the river. Okay, this is the river at the location. I wanted to know the speed of the river flow at that location. Then you probably had to use a vector function, right? So that vector function gave you the velocity corresponding to a location x, y, z, right? So that's the idea, basically, how you can apply a vector function in real life. Okay, yeah. So what we wanted to go over it here is basically I want to go over some typical mathematical operations functions. So for scalar function, we learned derivative, integrals, right? And so we want to apply the similar things and to look at the derivatives, integrals for vector function. And we also want to look at what's the meaning behind the derivative or even the integrals for a vector function here. Okay, yeah. So that's the idea. So let's take a look at basically common operations for vector function. First, let's look at derivative. So let's look at derivative of vector function at here. I'll write down a definition at here. We'll actually come back to the definition probably today or next lecture. Okay. So given a vector function r of t, its derivative is defined as derivative, right, dr over dt, okay, and equal to the definition, formal definition for derivative, very similar, okay. So r t plus delta t minus r of t over delta t, and then delta t goes to 0. That's the formal definition, right? So if you look at the definition of the derivative, think about the definition to a derivative scalar function. Essentially, the format is the same, except we're replacing a scalar function with a vector function now, right? Okay, yeah. We can also illustrate the idea here. So remember, this vector function r of t can be a parametric equation. So that could be a parametric equation for a certain curve. Okay, then basically, if I look at let's say if this is your r of t at here, okay, if this is r of t, then after certain time duration, then it travels to here. So that's r of t plus delta t, right? So according to the definition at here, it's this r of t plus delta t minus r of t. So it's this vector minus what? This vector at here, right? Okay. So that basically give us which vector? Give a vector from here to here. Okay. Yeah. So this vector to here, you can call that, okay, delta r, for example. Okay. So the delta r replace that to the top of the expression. So delta r over delta t. Then you let delta t goes to 0. So that basically when we use a small delta sign, right, it means it's a very small quantity. It's a still measurable small quantity. But if you let the delta t go to 0, then this quantity will become straight d, right? So this little delta will become a straight d. So the straight d is an infinitesimal small quantity now, right? That's mathematical, so not physically measurable. So that's derivative, okay? Yeah, that's derivative. Now, specifically, if your r of t, suppose that r of t okay, you can express the r of t. You can express that as a parametric equation for x, y, z. Then, when you calculate this derivative, all you need to do is basically you calculate the derivative for each one of the component. So that's basically dx over dt at here, plus dy over dt, dz over dt. Okay. That's basically is how you calculate the derivative of this vector function. Is that good? Yeah. Okay. Okay. So the other thing we'll shortly come back to this one in here. Okay. R of t at here, okay, is basically what type of quantity? It's a position vector, isn't it? Right? It's a position vector. Okay? Yeah. So when you take the derivative of the position vector with respect to time, what do you expect to get? Velocity, right? Yeah. Okay, so we'll come back to this one here. It's just like when you take the derivative of displacement, you get the speed, right? Okay. Okay, so let's take a look at a very quick example here, and then we'll move on to the next section here, okay? Okay, so here is a vector function, which is basically it's a parametric equation. Okay. It's a vector function at here, and I want you to calculate its velocity and also calculate its acceleration. Okay. Yeah. So before you move ahead and do the calculation, if you look at this vector function at here, okay. So based on what we learned from previous lecture, can you visualize this parametric equation or this vector function in 3D space? What does it look like? So x is this, y is this, and the z is this. Anybody? A spiral, yeah, right? It's a spiral here, okay? It's just the z component here, instead of it's a proportional to the time t, it's a t squared. So basically, every turn, it actually will, the pitch, right, will actually increase non-linearly. Okay. Okay, so this should be a very simple derivative exercise. All you're doing is just to calculate the derivative twice in a row. Okay. So if we do the calculation dr over dt for the first one, that's derivative first one is 3 sine t. Derivative second one, derivative first one is negative 3 sine t. The second one, 3 cosine t. The third, right, this. That's your velocity. Okay, so if you think about a particle moving along the spiral, then at every location along the spiral, there's a linear velocity, which is represented by this vector right here. Okay? Now, if we do another integral, another derivative here, so basically now we're doing it. It's a second derivative of the position vector or the vector function r. Okay. So one more derivative with respect to this velocity v. So that's your acceleration in here. Right? That's your acceleration. Yes. Good. Yeah. So next 3 cosine minus next 3 sine. Okay. So here comes a very simple question in here. So you have a velocity, you have an acceleration, right? Okay. So the question here is, at what time? Okay. So basically, at what time moment t, this v and a acceleration, they are actually perpendicular to each other. So how do we do this simple question here? So perpendicular basically means the two vectors are going to be what? The dot product equal to 0. Okay, good. So which means you just go ahead and calculate the dot product. Dot product calculation. You got all the two vectors here, so that's pretty simple. So negative 3 times sine t times negative 3 cosine t. Negative negative become positive. And the second part is 3 cosine t times negative 3 sine t. That's a negative. And so they actually cancel each other. So basically, your v dot a, okay, will simply equal to 2 times 2t equal to 4t. So your v dot a equal to 4t. And you want this quantity to be 0, so you set it equal to 0. So the only solution is what? T equal to 0. Okay, so 0. So basically means only at the beginning point your acceleration and the velocity are perpendicular to each other, right? Yeah. As a matter of fact, okay, if you substitute the t equal to 0, okay, back into the v and a, and you will be able to draw this. You'll be able to draw the vector out, right? Yeah. So that's essentially how you can visualize this whole thing in here. Okay. Any questions here? It's all good. Okay. So that's derivative, right? And then just a couple properties here. Okay. So it's just some rules on derivatives. These rules are fairly actually intuitive, okay, if comparing to the rules of derivative for scalar functions. Okay, so I'll just maybe write down a couple of it here. Really, you don't need to. It's very straightforward. So let's say if we're taking derivative. We're taking a derivative of this function. Okay, so I noticed in the past some students are not quite used to the way when we write a derivative like this. So basically, you see the first section portion in here. I have a d over dt, and then a big bracket. Inside the big bracket, there's some sort of a function at here, right? Okay, so that basically means this is an operator. Okay. This is an operator. So you're taking derivative for anything inside the big bracket. So in this case, it's like a product rule. It's like a product rule here, except this is a product between a scalar and a vector function. But the product rule actually still applies. Okay, you can apply the product rule as usual. So f prime times u of t and plus f of t times du over dt. Okay. So I guess the other thing I also want you to get used to is this. When you write a derivative, there are 3 different ways of writing a derivative, right? What are the 3? So let's say I have f of t. It's a derivative. You can write it either as df over dt, right? That's a very formal way. Or the other way is f prime of t. And what's the third one? That's right, right? So f dot t. Okay. But the last one, this one here, this is called Newton's notation, right? Usually, you only use the last one when the function is a time function. Okay. So basically, if a function of something else like theta or something, not necessarily you will use this one here. Okay, so you only it's a time function and you use it f dotted here. Okay, yeah. So if you see I have a mixture of notations, that's fine, right? Yeah. Product rule could also be applied, okay, to vector functions in a format like this. For example, if we have a cross product, okay, of 2 functions, because when you talk about vector functions, the product of vector functions actually is different from the product of scalar functions, because it involves what, either a dot product or the cross product, right? So that's the product meaning for vector functions. Okay, so this is a cross product. Then you can still apply the product rule. Okay, in this case here, very much the same. Okay, except you're doing cross product now. Okay, so you can change the cross product to dot product, and you basically you're doing the same thing as apply the product rule property or rules here. Okay, and the other one. A typical one is a chain rule. So if you have a vector function, it's a function of x, then x is a function of t, so it's basically it's embedded things here, right? Then this is where you can apply the product rule, because ultimately you're calculating the derivatives back to the t. So chain rule basically tells you you can take the derivative of this vector function u with respect to x first, and then you take the derivative x with respect to the t. So that's the chain rule. Okay. Yeah. So other than that, basically it's all the same. Okay, in terms of derivative rules. Okay. Yeah. Okay. So let's quickly look at one example, and then we'll move ahead. Okay. Okay, so I have a v and a u and a v at here. So these are they are two vector functions. Okay. So can you try to calculate calculate this derivative? So derivative of the dot product u of t dot v of t here. Okay. Yeah. So in this case, okay, so when you your first intuition, you actually probably what you wanted to do is you want to finish the dot product first, right? And then you calculate the derivative. But I want you actually to try a different way. Okay. I want you to basically use this product rule at here to try this way. Okay. So calculate this derivative using the product rule, and instead of a cross product, it's just a dot product here. Okay. Yeah. So try this one, and then and then you can always verify the other approach, right? So this is what I want you to try here. Okay, the product rule applied to this expression here. So you calculate the derivative of the first one dot the second one, then plus the first vector dot derivative of the second function. Okay, so you go ahead, you try it. Okay, it should be fairly straightforward. Okay, with a little bit careful calculation, you should end up with the answer 3t squared plus 2t minus 3. I really wanted to try is to verify is, so how about you do the dot product first and then calculate the derivative, right? So basically if you do that, okay, so what's the dot product here? T times t, so t squared plus t cubed, and then minus 3t. Right, so that's if you calculate this way. Then derivative of this whole chunk, t cubed. Okay, and derivative of this whole chunk here will give you this exact same answer, right? Okay. Okay. Good. Okay. All right. So let's take a look at another example here. Okay, look at an example. This is an example that's very much related to a particular dynamic problem. Okay, so in dynamics, there's a very common problem. Basically, you have a particle, okay, moving along the circle and along a certain axis at here, for example, right? Maybe moving at a certain angular speed omega. Okay. Yeah. So maybe it's a circle centered around an origin. Who knows, right? Okay. So in this particular type of dynamic problem here, what we learned is, okay, so if this is the position vector, okay, if this is the position vector representing this moving particle, okay, and then you have your velocity at here, right, basically representing this particle at here, okay, representing the velocity particle. So one thing that we learned is, okay, this v at here, okay, this v is actually perpendicular to the position vector, okay, perpendicular to position vector. So basically, if there's always a motion around a circle, right? Circle basically means the radius, right, is always a, okay? Then the velocity is perpendicular to the position vector, okay? Position vector. Okay. It doesn't. This relationship doesn't hold true for any other general motions, right? If you have a curve and then if you are moving, so there's a velocity, but doesn't mean the velocity will be perpendicular to the position vector, right? Yeah. So here's a simple question: how can we prove that the velocity is actually perpendicular to the position vector, right? How can we prove that? Okay. Yeah. So we'll try to prove this one here. Okay. So basically, and why is it perpendicular, right? Mathematically. So let's formulate this question in here to the way that we can manipulate, right? So this is a particle moving along a trajectory, and what's the nature trajectory? Nature trajectory is its length for the position vector is always what? It's a constant. Okay. Yeah. So basically, in this case, here, this position vector r, okay, it's a constant. So let's say maybe I use a. So let's say use a at here. Okay, use a. So that's essentially the nature of the motion, right? So okay. So then I call this basically vector function of constant length. So let's start from this expression in here. When you write r of t equal to a, so this is representing in here is what is the absolute value or the length of the vector, right? The length of the vector here. So what's the length of vector? Length of vector, if you read it, your r of t is given, so basically it's x of t plus y of t squared and plus z of t squared, right? That's your length, okay? Yeah. Okay, that's the length set here. And then what happens at here is, if you recall that, okay, if you recall that the definition of the dot product, okay, when you use r dot r, I guess what does it give you? No, 1. Well, r is there's actually no trick out here. So here's x, y, z. Okay, this is a vector, right? So you basically use the vector dot itself. So mathematically, what does it equal to? Yeah, so x squared plus y squared plus z squared. Okay, yeah. And that happened to be basically the length squared. Okay, the length squared. Okay, is that good? Yeah. So then come back to this formulation in here. So here is my motion, right? Representing the particle. Here's the motion in here. So basically now you look at this guy here. If I take a square of both sides, okay, it doesn't change anything, right? Doesn't change anything. But then on the left side, according to the notation now, I have r of t dot r of t equal to a square. Okay, so now basically the original expression is rewritten slightly different. So in terms of dot product now. Okay, yeah. Then at this stage, so what we're going to do is we're going to take a time derivative, okay, or derivative with respect to the t for both sides of this expression. Okay. So basically, we're going to take the derivative of both sides of this expression. Okay. Yeah. So your right side is a constant, and then the derivative must be 0. Okay. And your left side, it's a d over dt bracket something dot something. Well, that happened to be exactly what we just practiced, isn't it, right? We can apply what? We can apply the what rule? The product rule. Okay, so let's apply the product rule here. So when you apply the product rule, you have dr over dt dot r of t, then plus r of t dot dr over dt. Okay, that's the product rule for the left side. Okay. Dot product is a commutative. Basically, a dot b is the same as b dot a, right? So when you look at these two expressions, they actually what? The same thing, isn't it, right? So basically, you get 2 times r of t dot dr over dt equal to 0. Okay. And 2 divided by 2 for both sides, so that actually is gone, right? You don't need that anymore. It doesn't play anything. So now you end up with a simple expression. So r vector dot its derivative equal to 0. Then according to the dot product property, when two dot product are when two vectors dot each other equal to 0, that means the two vectors must be perpendicular, right? So that must be r is perpendicular to this. And dr over dt is basically the velocity vector. Okay. So that's why the velocity is perpendicular to the position vector when you have a vector function that's constant length. Okay? Yeah. Or when you have a circular type of motion, right? Yeah. So this is a very useful results. We actually will use that very shortly, okay, afterwards. But just bear in mind that this nature here. All right. So let's look at this is about the derivative of vector function. So let's look at the next one. Let's look at the integrals. Okay, so let's look at the integrals of vector function. Okay, so if you're given a vector function r of t, okay, and you're required to, let's say, calculate its integral. So this is an indefinite integral here. Okay, so the limit's not given. You're calculating this integral r of t. Okay, then all you need to do is you just have to calculate the integrals for each one of the components at here. And don't forget this I hat, g hat, k hat. Okay. So integral of a vector function is still vector. So it's still going to come up with a vector. Okay. Just like derivative. So derivative vector is still a derivative. Okay. So that's how you calculate the integral of this. when you calculate the integral of a single function or scalar function, we have this concept called antiderivative, right? So now let's basically apply the same concept. Suppose that this r of t, okay, is an antiderivative. Okay, it's an antiderivative for r of t. Okay, so then the derivative, the integral of this r of t is basically equal to the antiderivative. And then what? Plus a c. Plus a c. So that's where you got to be careful here, because we're talking about it's a vector function. So instead of a constant, it actually should be what? Should be a constant vector. Okay, yeah. So that's the corresponding part, for integrals of vectors. Of course, you only put a c here because this is indefinite. There's no limits, right? If there's limits, then you don't need that c there. Okay. Yeah. So I think this is quite straightforward in terms of integral. There's really nothing to exercise it here. If you're given a vector's functions, all you need to do is just do the integrals as you practiced on the scalar functions, right? So there's no difference at all. Okay, so now let's put things together, right? Let's put things together. Basically, we'll look at three very useful concepts, okay? Mostly involving the derivative. So let's look at three useful concepts. And they basically we'll look at the three different vectors. So tangent vector, a unit tangent vector, and then unit normal vector. Okay, so we'll look at the different vectors here. There's another one here. At the end, we'll look at it's basically called binormal vector. Okay, so we'll look at what it is, but so we'll look at the tangent and the normal vector first, and then at the end, we have another one called binormal vector. Okay, so very useful vectors. So let's look at the most easy one, the easiest one here, which is a tangent vector, right? Okay. So I'm going to draw something in here. Okay. Here is the vector function r of t at here, describing a certain curve C. Okay. Then we already learned, okay, basically if r of t is x of t, y of t, and z of t, okay, and then the dr over dt, which is its derivative, okay, which give us dx over dt, okay, dy over dt, and dz over dt. So this guy here, okay, it's basically the tangent vector we're talking about, okay, which is a velocity vector. Okay, so the position vector's derivative give a velocity vector, and the velocity vector, it's a tangent vector. So that tangent vector, basically it's a vector, okay, tangent, okay, to the curve C. Okay, so that's a tangent vector T. Good. And you can actually sort of understand why is it tangent. So using this graph, remember when I derived the derivative, I used this graph here, right? Yeah. So you can imagine, okay, as delta t is becoming infinitesimal small number, so that vector here will become a tangent to that at that point. Okay, at that point. Okay, so that's very normal. That's a tangent vector here. Okay, that's how you calculate tangent. From the tangent vector, this is basically the next one is a useful one here, unit tangent vector. Okay, so unit tangent vector. Unit tangent vector, if you already have this tangent, if you will use a t hat, right? If you already obtained the tangent vector, then all you need to do is just to normalize it. Okay, just to normalize it to get this so-called unit tangent vector. Okay, yeah, so that's unit tangent vector, representing the direction of the velocity, right? Okay. Okay, so now next one here, let's look at basically the so-called principal unit normal vector. Okay, yeah. So I'll approach this just basically through two different type of directions here. Okay, yeah, two different type of directions. The first direction is more or less just pure mathematical meanings here. Okay, so let's come back to the unit tangent vector. Okay, unit tangent vector. What does unit mean? Basically means what? Its length equal to 1, right? Okay, so this is a vector of a constant length, isn't it? Right? That's exactly the example we just gone through. So t hat is a vector constant length is 1. Then I can apply the results from that example, which is t hat t dot what? dt hat over dt equal to 0, right? Equal to 0. So that's from the previous example, right? Okay. Yeah. Okay. So now you look at this this relationship here. Basically saying you have a t hat that is perpendicular to this vector here. Okay. So perpendicular to the dt hat over dt. Okay. Then what we do is we let this n at here. We let a new vector. Okay, let it equal to this dt hat over dt. So this one here we call it normal vector. Okay, so be careful that this is just a normal vector, but it's not what? It's not unit normal vector. Is that clear? Because it's very confusing. Because why? What is t hat? T hat is a unit vector, isn't it? Right? So you might very well think that the derivative of a unit vector give me a unit vector, but it's actually not. Okay. So derivative of a unit vector doesn't necessarily give you a unit vector. It doesn't give you a vector, but it doesn't necessarily mean it's a unit vector, though. Okay. Yeah. So that's why here what's this? So that's why here I call this as just a normal vector instead of a unit normal vector. Right? Yeah. But what we do want is what? We do want a unit normal vector. So basically, okay. So basically, what do? We can just simply normalize this normal vector to get a unit normal vector. Alright, so that's how you can get this so-called unit normal vector or principal unit normal vector. Okay. Yeah. Is that good? Okay. So this is essentially one way how you can derive at this so-called unit normal vector here. Now the other way of deriving here is more or less just to through this derivative concept here again. So let's say if I have a curve, okay, let's say if I have a curve like this, and then suppose that at this moment we have a t hat, okay, like this. So we have a unit tangent vector pointing to this way, or the velocity pointing to that way, right? Yeah. And after certain time moment, let's say it comes to this one now. So it will become t plus delta t, okay, plus t delta t. So now I have t hat and t hat t plus delta t. So I'll move the two vectors, okay? I'll move the two vectors to something like this. Is it okay? Right? Yeah. Then this is t hat t plus delta t. This is t hat t, right? T hat t. Okay. Yeah. And then we can create a vector between these two, okay, like this. Okay. So this one at here, okay, you can create a vector at here, right? You can create a vector. Okay. So according to the basically the normal vector at here, you see that dt hat over dt. So look at this derivative. So what does that mean? It basically means what? It's the limit, okay, t hat t plus delta t minus t. So this vector minus this end of this vector, isn't it, right? And then divided by this time here. Then you let the time go to 0. That give you the normal vector here. That give you this normal vector nt, okay, the nt, okay, which is basically, okay, this vector, okay, which is basically this vector. So mathematically, if you want to derive, you can derive this. Then you normalize this n of t, you get this n hat, okay, n hat. So if I come back to this curve, right, come back to this curve, as delta t approach to 0, okay, as delta t approach to 0, now ultimately what you end up with at this location is what? You end up with, at this location, you have this n of t at here, right? At n of t. And the n of t is perpendicular to the t hat. And of course, you can normalize this n of t to give you n hat of t. Okay, so that's what the unit normal vector actually means in here. Okay, actually means. So physically, right? If you look at this t hat and an n hat, so physically, what does t hat represent? So the t hat is what? The direction of what? Velocity. Good. And then this n hat, okay? It's also direction, isn't it? Okay, it's not direct. It's not direction of acceleration. It's the direction of turning. Okay. So essentially, it'll tell you which direction it's going to turn, right, along this curve at here. So that's what the n hat really. What it does, okay? So really what it does here. Is that good? Okay. So unit tangent vector, unit normal vector. Last one. Binormal vector. So the binormal vector is defined as, okay, this is defined as b hat. and the b hat is equal to t hat cross n hat. Okay, cross n hat. Okay, so let me illustrate this one here now. You probably say, okay, so two unit vector cross each other. It'll give you another unit vector, right? Yeah, give you another unit vector. So if I illustrate this one here, for example, if we have see that if imagine this is a curve in 3D, right? Okay, then if this is a t hat and this is n hat, okay, so the b hats use what? The right hand rule. In this particular case, it's a little bit awkward, so that's actually going downwards, right? That's the b hat. Okay. If you draw it at here, okay, so that will be this way. Okay, yeah. So the length is a bit of exaggerated. Okay, so that will be the b hat. So often in time, okay, if you look at this t hat, b hat, n hat, what does that actually strike you there? What does it remind you? We have been using it quite planes, normal to each other. Yeah, yeah. Actually, it should remind you what? We've been using it, writing it all the time. We're writing I, J, K, right? I, J, K. So 3 unit vectors basically. Okay. The nature of the 3 unit vectors that are here. You see that? That's, you can consider this as I, J, K, isn't it? Right? Consider it I, J, K. So that's actually basically called TNB frame. Or better yet, there's a name, okay, called Freenet Surret frame. Okay, it's a frame. Okay, it's for this time, typically your IJK, right? Your IJK is a frame associated with XYZ coordinate system. That's a coordinate system. Maybe it's a reference frame. It's fixed. But if you consider there's a point moving along this curve, okay, then you can always imagine there's a frame associated at that point. You can create a frame system using this TNB frame system to represent there's a frame moving along that curve C, right? Imagine that. Okay, so that's basically, it's a very useful one. I was actually trying to get a simulation ready from one of the robotic system, but somehow there's some problems with MATLAB was updated or something. But basically, in robotics application, you know, you always have a hand, right? Okay, so how do you basically define where you want it to go and how you want it to go? Okay, so you want it to go here, that's easy, right? But as a hand, you can grab this like this, grab this like this, grab this, you know, differently, isn't it, right? So that basically is defined using a frame attached to the gripper. Okay. So that frame is, for example, can be a TNB frame. Okay. It's a moving frame. You can define how the frame is oriented with respect to the reference frame. And then you can basically define the motion of the gripper at here, okay, as the robot is moving. Okay. Yeah. So it's a very useful one. Okay. For example, if I have, let's say, if I have a spiral curve. Okay, I have a spiral curve. Okay. So you can imagine at each location on the spiral curve, and you would have basically a TNB frame associated, right? TNB frame associated. So that's somehow you can use that as information for some sort of a manipulation. Okay. Yeah. And the other thing that's quite useful, you actually probably have seen that in your dynamic course. Okay. So if you have a curve C at this location, your acceleration, for example, may be pointing to that direction, right? Pointing to that direction. So what's the very common operation you do? You would what? You would decompose that. You would decompose that. You would decompose the acceleration into two components, isn't it? Right? One component you would call that. You decompose that into the into this tangent direction, and the other direction you would decompose is is the normal direction. Okay. Yeah. So that's two directions you would very well decompose that. So basically, your A, you can rewrite it as the tangent direction times t hat, and then the quantity of that times the n hat, right? Times n hat. Good. So that's the T and B frame, very useful one. Okay. So whenever you got a curve, okay. So something that you need to bear in mind about this is essentially the T and B frame. So let's do an exercise at it here. Okay. All right, so we have a curve, okay, over here. It's a vector function. Let's calculate the unit tangent vector and the unit normal vector. So this is somewhere that in this course it'll be a moment of truth to check your skills on calculating the derivative functions. Okay, yeah. So you may think this is easy, but once you carry out this to the second order derivative, and often in time you'll find it things are getting a little crazy. Okay, yeah. So let's go over a few steps at it here. Okay. So we need a t hat. So to calculate t hat, we calculate the tangent vector first. Tangent vector is basically the derivative of this position vector. Okay, which is velocity. So that seems easy. So that get 2t plus 3 plus 0. Okay, so it's a tangent vector. Then unit tangent vector is to normalize it. Okay, so to normalize this tangent vector. Normalize basically means you divide everything by its length. So its length is 4t squared plus 9. Okay, and then 2t 3, like this, right? Okay, that's unit to tangent vector. Okay, so everything so far so good. It seems to be very straightforward, right? Okay. And then you calculate its normal vector, unit normal vector. Okay, so you look at the unit normal vector formula, which is which is this one. That's your formula for unit normal vector. So what does it involve? It involves calculating the derivative of this unit tangent vector and also its length, right? So apparently we have to calculate the derivative of the unit tangent vector here. Okay. So basically we need to calculate what is this guy. Okay. So here is your t hat, and then you need to calculate this unit tangent vector derivative. And this is where I typically will see a lot of mistake to happen now, because somehow, but by looking at this derivative, you have two components, right? X of t, y of t. So, and that basically equal to dx of t over dt
plus dy of t over dt. Okay. Then the dx of t over dt. Okay. Okay. Look at this one here. It's d over dt 2t over 4t squared plus 9. Okay. And that seems to be a simple one, but actually a lot of mistake can happen in here. Okay. Yeah. So this is the time you need to brush upon your derivative skill. Okay. So we're almost running out of time, but just think about the direction. What would you do, right? Well, how would you calculate the derivative of this one here? What does it remind you? Quotient rule, that's right. So then the first question would be, what is the quotient rule, right? Because I was asked quite often, actually, in even exam, can you write down the formula for quotient rule? So so it's something that you have to remember it, right? So this is the quotient rule here. Then you look at this formula, you look at the actual case. So that basically means the v equal to 4t squared plus 9, and u equal to the 2t, right? To 2t. Okay. So this is the time we apply the quotient rule. Okay. And we're going to just apply the quotient rule here now. V squared, you get 4t squared plus 9. U prime times v. What's u prime? U is 2t. So derivative of u over t is 2 times v, 4t squared plus 9, minus v prime times u. So u is 2t. Let's put the u of here. V prime, what is v prime? V prime is dv over dt, right? So this is a v at here. So then basically, what is the dv over dt? There's an inherent chain rule here, basically. This is actually where I see sometimes mistake, right? I see a mistake here, okay? Yeah. What's the derivative of this one here? 1/2 4t squared plus 9, negative 1/2, and then times what? 8t, okay? Yeah. So plug it over here. So 1/2 4t squared plus 9, negative 1/2 8t. You don't actually stop here. Okay, this looks like you're finished, but you don't actually stop here. You actually need to simplify this. Okay, you need to simplify this because you do need to calculate it further. Since I'm running out of time, so I'm going to write down the results here. You can try yourself, and I'll try to go over this a little bit in the next lecture. Okay? Yeah. Okay. So any questions? Okay. All good. Yeah.